Hi, my name is Chris Baker. I'm the Program Executive within the Space Technology Mission Directorate for the Flight Opportunities and Small Spacecraft Technology programs. I also support the Space Technology Mission Directorate with strategic planning for small spacecraft technologies. This chart here depicts our envisioned future for small spacecraft capabilities. The items on this chart will not be a surprise to the small spacecraft community and will probably also not be a surprise to the space community at large. We see small spacecraft and responsive launch as capabilities that help us bring technology rapidly from the lab into an orbital or suborbital test environment, helping us rapidly mature those new capabilities and enable them to be infused in future missions. Small spacecraft are already emerging as an important part of terrestrial infrastructure for communications and navigation. We see those capabilities being extensible to the deep space environment, with small spacecraft potentially serving as communication, navigation, and timing nodes for missions around the moon, potentially Mars, and other destinations beyond Earth. Small spacecraft are already providing unparalleled sensing capabilities for Earth science and other terrestrial applications. We also see those capabilities as being extensible to deep space, including for heliophysics and other situations where a swarm of nodes of 30 to 100 spacecraft provide value for temporal and spatially dispersed measurements. We also see those capabilities as being very valuable for synthetic apertures and other applications for Earth science, planetary science, potentially astrophysics, and others. We also see small spacecraft as a capability that can be used to make targeted measurements around the moon, Mars, Venus, and the asteroid belt or other destinations within the inner solar system at lower costs and faster speeds than previously achievable. In order to achieve these envisioned future states, there are a number of technologies that we believe need further investment. Here on this chart are a few of the top ones that we currently see as priorities. So high delta V, small spacecraft propulsion systems, deep space orbiting maneuvering vehicles, and in particular expanding the capabilities of emerging commercial orbital tugs to the deep space environment. InSpace Autonomy for small spacecraft and distributed systems, interoperable networking for small spacecraft communications and PNT systems, small spacecraft proximity operations and abort systems, and responsive launch for both suborbital and then also access to orbital test opportunities. The state of the art for small spacecraft is rapidly changing. But right now, the need that we see for high delta V propulsion systems is to evolve systems that are currently typically able to produce hundreds of meters per second of delta V, and soon perhaps up to almost 2 kilometers of delta V at the nanosatellite scale, and expand those into low size, weight, power, and cost systems that are capable of imparting 5 or more kilometers of delta V at the microsatellite scale. These systems need to be highly manufacturable with repeatable performance and also be compatible with the deep space environment. This helps enable missions to the moon, Lagrange points, Mars, Venus, near-Earth objects, as well as longer duration and more responsive missions in Earth orbit, including those at lower altitude or requiring plane changes. Small spacecraft represent cost-effective mission options, but the propulsion capabilities within the size, weight, and power constraints of a small spacecraft can be a challenge. To achieve the desired 5 or more kilometers of delta V, the propellant throughput and the system life of many current nano and microsatellite propulsion systems will need to be increased. High efficiency propulsion, such as electric or dual mode, will likely be essential to meeting these size, weight, and power constraints. Non-traditional propellants, especially those that are green or start as solid metals and are then vaporized, or water that is either electrolyzed or used as steam, may provide greater compatibility with lower cost launch opportunities. We believe these systems that will be developed for terrestrial Earth orbiting applications will need some modification in order to enable them for use beyond Earth. Yet, we do not want those modifications for deep space applications to so significantly modify the systems that we cannot take advantage of the scalability of the manufacturability of these systems. So for deep space orbiting maneuvering vehicles, we see that there are a number of orbiting maneuvering vehicles or space tugs that have been deployed or are in processing for near-term deployment for Earth orbit applications. Higher performance OMVs with about 5 kilometers or more of delta V are anticipated in the near future. What we are looking for here are vehicles that are ultimately capable of 10 or more kilometers of delta V and then can provide services to the deployed spacecraft, such as position, navigation, and timing, that can act as communications relays, and or host payloads on board as the primary spacecraft or supporting spacecraft for that mission. So this enables expansion of small risk-tolerant missions further beyond Earth. It enables missions to reach multiple destinations from a single launch or achieve multiple orbital plane changes. Also helps missions reach non-traditional orbits and those beyond the Moon, Mars, and Venus. Emerging systems, such as small launch interplanetary transfer stages, may require increased capabilities to achieve this 10 kilometers per second target, and systems being demonstrated for Earth orbiting applications may require modification and testing to de-risk them from multi-year missions and deep space operation. And then adding these additional services such as PNT and communications relays to OMVs can significantly increase the operational capabilities of low size, weight, and power spacecraft and for distributed missions at multiple deep space destinations. Then again, those vehicles themselves can host payloads and act as the spacecraft bus for a number of instruments or other technology payloads. InSpace autonomy for small spacecraft and distributed systems is another area of importance. Most current constellations use ground-based and semi-autonomous scheduling and orbital maintenance to decrease human-in-the-loop operations, but many of them still upload commands to each spacecraft individually. Newer systems are moving more autonomy into the space element, but still rely on updates from ground-based systems. For future missions beyond Earth, we are going to need a significant reduction in ground station aperture time for single spacecraft missions and increased autonomy that allows tens of spacecraft to be operated as a single unit beyond Earth. This helps enable large distributed missions such as sensor webs for heliophysics, advanced Earth orbiting missions that can operate without ground stations in the loop, and single spacecraft autonomy can enable near lights out operations for missions beyond Earth. So small spacecraft, we believe, are uniquely suited for large distributed missions, but operations are prohibitive without autonomy. InSpace autonomy can assist with missions with communications limitations or that need to react to sensor data, often without humans in the loop. Commercial software architectures and modules that are part of other U.S. government and non-NASA distributed missions can be adapted for use by NASA missions and operational environments relevant to NASA. And then to enable multi-point measurements beyond Earth, tens of spacecraft must be operated without saturating cross-link or ground-link bandwidth. Autonomous coordination allows small spacecraft to be configured in space as virtual telescopes and distributed apertures for investigation of Earth and other objects of interest throughout the universe. And then single spacecraft autonomy can address communications limitations and enable more robust situational awareness, fault recovery, and science data collection. Autonomous spacecraft can help enable responsible utilization of popular or congested orbits, providing benefits to all users of those orbits. And autonomy can enable dynamic reconfiguration of assets for Earth observations. So to help enable those capabilities, small spacecraft communication, position, navigation, and timing services require additional investment. So space-based assets in Earth orbit currently provide global PNT and communication services for terrestrial activities and to many small spacecraft in low Earth orbit. For lunar missions, PNT and communications are currently provided through large terrestrial-based dishes, such as those employed by the NASA's Deep Space Network. For the future, we envision small spacecraft that can be deployed to the moon and to deep space destinations that provide global lunar comprehensive PNT and communications relay infrastructure. This, we believe, can help address the strain on current terrestrial-based capabilities, particularly for tracking from future cislunar and deep space missions. We believe this offers options for cislunar and lunar surface missions where direct communication with Earth-based systems will not be available. So low size, weight, power, and cost, deep space communication, navigation, and timing synchronization will be critical for missions beyond Earth. While use of multiple spacecraft per aperture capabilities that are being developed by the Deep Space Network can help service a growing number of concurrent missions, peer-to-peer navigation, paired with DSN tracking or emerging capabilities such as use of weak signal GPS or one-way ranging can help play a role in servicing the position, navigation, and timing needs for those missions. We also envision that those future spacecraft should be interoperable. And so interoperable networking for small missions is another area where we believe there should be a focus. So delay-tolerant networking is in use by NASA missions. The hybrid space architecture concept has been adopted by the Department of Defense and commercial companies as a variable trust network for rapid and secure data exchange across both U.S. government, international, and commercial space systems. And then the NASA's SCAN office developed draft interoperability standards for a concept known as LunaNet. For the future, we see increased interoperability between government and commercial space networks, and we believe we need operational interoperability protocols that help pair the NASA LunaNet concept with the hybrid space architecture and existing capabilities like delay-tolerant networking. So this, we believe, enables ubiquitous communications between in-space assets, airborne systems, in-situ sensors, and ground assets. In cislunar space, we believe this will enable a network of surface and orbital nodes, low size, weight, and power cost relays, and more capable assets that can serve as hubs connecting to Earth-based communication networks. One of the areas of interest for use of small spacecraft is as inspection vehicles or delivery vehicles for higher value assets. However, in order to feel comfortable placing what is generally considered to be a low or cost, higher risk tolerant system in close proximity to a high value asset, new technical capabilities are likely needed. So currently, technology demonstrations at the small spacecraft relevant scales have been conducting on-orbit servicing and inspection, with several more demonstrations coming up. However, for the future, we think we need to de-risk low size, weight, and power and cost proximity sensors, software, and then reliable proximity abort systems that, if there is an issue, can safely remove the small spacecraft from potential collision with that high value or inhabited asset. So we need to reduce the risk of use of small spacecraft in proximity to those high value assets. These systems can also enable small spacecraft missions to natural targets like near Earth objects or other missions requiring persistent formation flight. We do believe that small spacecraft can be well suited to play roles in inspection, servicing, and other proximity operations with either inhabited or high value assets, as well as asteroids and other small bodies. So the use of lower risk tolerant spacecraft in proximity to risk intolerant assets is possible, we believe, if the small spacecraft is equipped with a sufficiently robust proximity operations abort system that will reliably prevent collision in the event of a failure. And for that, obviously, we also need those proximity sensors that can determine the relative positioning with those other assets. Those systems, once developed, could also be outfitted on orbiting maneuvering vehicles and then can help those serve as delivery, especially kind of the last mile vehicles for high value assets for servicing and resupply. Finally, we also believe that responsive access to suborbital and orbital space is going to help enable not just all of the technology development that we just talked about, but also technology development across areas of interest to NASA, other government agencies, commercial partners, international community, and universities. So commercial suborbital vehicles are currently providing valuable flight test capabilities for technologies that are relevant to exploration, discovery, and space commerce. For the future, we see additional vehicle performance and payload accommodations, including payloads hosted on recoverable orbital launch vehicle stages and greater access to orbital platforms for hosting technology testing. So rapid advancement of capabilities requires frequent opportunities to test and evaluate new technology in an operational environment. Embracing the fly, fix, fly, and agile aerospace practices allows technologists to rapidly iterate through flights and failures to innovate at a pace that is impossible in a less risk-tolerant environment. So advancement and additional access to commercial suborbital and low Earth orbit capabilities can further expand NASA use of rapid and lower cost commercial space flight for technology development and demonstration. So looking for higher altitude suborbital flights, or the ability to host payloads on recoverable orbital rocket stages. That could provide longer duration microgravity as well as access to speeds and heating conditions more relevant for planetary entry and re-entry testing. Routine and affordable hosting of small payloads on orbital platforms in low Earth orbit can provide NASA-sponsored research with rapid access to longer duration testing in relevant environments. Through frequent low-cost access and increased capabilities, such as variable reduced gravity testing, high-altitude balloon station keeping, and enhanced closed-loop entry, descent, landing testing, commercial suborbital vehicles can continue to expand their role as a critical tool in the continuum of space technology flight testing capabilities. Thank you very much. If you have any questions, please feel free to ask them through the RFI. Looking forward to your questions, comments, and other feedback. Thank you.